Okay, yesterday we left off here in lesson 1.5. In lesson 1.5, we were talking about parametric equations on the front. So when an equation that has x and y is defined with a third variable t called the parameter. And then we had talked about how to know what it means to be one-to-one. Remember, if it's one-to-one, it is a function, and it has an inverse. And that's what we were just testing up there at the top, that if it's a function, it passes the vertical line test. If it has an inverse, it passes the horizontal line test. And that's where we finished class yesterday. Today, example 4 is find the inverse function for each of the following if one exists. I'm probably only going to do about 2 of these. I don't think I need to go through and do all of them. But this is what we did back in Algebra 2. Okay, so this is not brand new. Been a while though. But in order to find an inverse function, this is where you're going to take the x and the y and you're going to switch them and then solve for the y. Now, in order to do that, first of all, what do you know about f of x? F of x is the same as y, right? So if we rewrite this equation right now, this is y equals x over x plus 1. Right? That's just me rewriting it that f of x is the same as y. Now, so in order to actually find the inverse, switch x and y. Everything that's an x becomes a y. Everything that's a y becomes an x. So when I do that, this equation becomes, instead of y equals, we're going to say x equals. Instead of x on top, it's now y. Instead of x plus 1, y plus 1. And so my step right there, and I'm going to write it off to the side, is that I switch x and y. That is the step I took, was to switch x and y. The other step, once you switch x and y, is to figure out how to solve for y. Okay, those are kind of the 2 steps we're taking. So, thoughts on how we can solve for y?
Well, you can't divide it because that 1 plus 1 is connected, right?
Right. As in, I'm assuming you're going with we can't cancel the y's is what you're trying, right? Okay, yep, that's exactly correct. Can't cancel those y's because the y on bottom is a y plus 1.
Can we do times y minus 1?
We're not, okay, I do want to multiply.
Multiply the numerator and denominator by y plus 1?
Y plus 1. Okay, well, not numerator and denominator, but we're going to multiply that fraction by y plus 1. So the question is, how do I get rid of a fraction? Means we want to get rid of the denominator. Yeah. That denominator means we are dividing by y plus 1 currently. So to get rid of dividing by y plus 1, we're going to multiply by y plus 1. If I multiply this fraction, or the right side, by y plus 1, that means I have to multiply the left side. I didn't leave room here. Sorry, guys. We're going to multiply that x by y plus 1. Sorry, very not readable.
So would you have to write that as y plus 1 plus x? Because you can't combine that with that.
How about, you can multiply. How do you multiply y plus 1 times x? That means you're going to take the x and we're going to distribute. Yep, good. So x times y is xy plus x times 1 is x equals, now what happens on the right side? Yeah. If we're multiplying by y plus 1, you can think of it as y plus 1 over 1. The whole point is that y plus 1s will cancel, leaving you with y. Okay. Again, my goal is to solve for y. So if I'm solving for y, I want my y's all on the same side. I already have a y right here. We also have an xy term that needs to join it. So to move a positive xy, we are going to subtract xy. If I subtract xy on the left, subtract it on the right. How do you guys feel about me flip-flopping my sides when I write my next step? So meaning I'm going to put y minus xy equals, and on the right we're going to have an x. Okay, we're almost there, but I'm out of room, so I'm going to bring this up here. Okay, this is probably the step that we're least familiar with, but we're trying to solve for y. We have two terms that we can't really subtract y minus xy because they're not like terms. How do we get that y to separate there?
Would you divide?
We will divide eventually. How do I get the y to pull apart from those two terms? Both terms have a y in common, yes? So can we think of that y as a GCF and factor it out? Do you see where I'm going with this? Okay. If the idea that I want you to do is we're going to factor the y out. If I factor y out, that means I'm dividing both terms by y, if you would. Okay. So y divided by y leaves me with a 1 minus xy divided by y leaves me with x. So by factoring that out, I have y times 1 minus x, and my right side of my equation still equals x. Okay, we're ready for our last step. This is y times that parenthesis. How do you get y by itself? What do you think, Ashley?
You divide by 1 minus x.
Since it's y times that quantity, we can divide by that quantity. So that means we're going to divide by 1 minus x. If I divide the left by 1 minus x, divide the right by 1 minus x. On the left, 1 minus x's will cancel.
So it's
Y equals x over 1 minus x. I'll be honest, this is a little bit more difficult problem. It's kind of probably not the greatest to start, just introduce this with, but it's good solving practice. Now, officially, to call this my final answer, what can I replace that y with now?
f of x.
F of x, except it's not f of x, it's f inverse of x. Because originally we started with f of x, we were finding the inverse. So I'm going to call this f inverse of x equals x over 1 minus x. Notice I did not cancel my x's because that denominator is a 1 minus x.
So f to the negative 1, which is the inverse, right?
Yes.
So x equals x over 1 minus x.
Uh-huh. How did I get this 1 minus x? Because
you can't distribute it into you have to keep it by itself, so you have to divide it. Like you can't distribute the y.
we factored out a GCF of y. Since both terms had a y in common here, I took the y, I put it out front, and when I factor something, it's like I'm dividing both of these terms by y. So right here, y divided by y became 1. xy dividing by the y becomes x. Okay? Okay. It's all right. Good questions here. Okay, let's go ahead and try the next one real quick. And then I'll probably skip C, honestly. Okay. Trying to find the inverse. What do you know about f of x?
It's y.
It's y. I'm just going to cross it out this time and write it as a y. Because, I don't really need to rewrite the whole thing. Okay, so how do I actually find the inverse? Flip the x and y. So instead of y equals, I'm going to say x equals. Instead of square root of 4x minus 3,
It's square root of 4y minus.
square root of 4y minus 3. So that was that first step of switching x and y. And now, solve for y.
Can we, the second sentence,
Okay, yeah.
or whatever you call it.
That y is under a radical. To get rid of a radical, you raise it to the power of the index. We're going to square it. If we square one side, square the other side. What is x when you raise it to the power of 2? X squared. What happens when you square the square root of 4y minus 3? Square and square root effectively cancel each other out, and I have 4y minus 3.
So since that's x to the square, are we going to write x plus 1 what? Or,
No.
Whatever. We keep it x squared?
We're going to keep it x squared. My goal here is to solve for y.
Plus 3.
So to get y by itself,
So, add the 3 over.
add the 3 over. And so now I'm going to have 4y equals x squared plus 3. And if it's 4y equals x squared divided by 3, or plus 3, we need to divide by 4. Now, 4y divided by 4 is going to leave us with y. How am I going to write that y in my final answer? You can say x squared over 4, or you can say 1/4 x squared, because there's a 1x squared. There's a couple different, you can write it as x squared over 4 plus 3/4. You can write it as 1/4 x squared plus 3/4, like I just did. You could even write it as x squared plus 3 all over 4. Now, if you haven't already, what can we replace that y with at the beginning?
Y. Yeah.
F inverse.
Yeah. And that's it, right? Nothing else to do.
Correct. See, that one was a much better one. I probably should have started with that.
It's kind of easy. It's just like it's a thought process.
Yeah, it's just, honestly, you got to switch the x and y. And once you do that, it's solving for y, which, I mean, you guys know your basic equation solving skills. So, it's just using those and solving.
Yeah.
Okay.
But if we were to write x squared over 4, you wouldn't count it wrong, would you?
No, I would not.
It's the same thing.
Correct. Yep. And unless we have a reason to, as I said, I would even count x squared plus 3 all over one denominator of 4.
Oh, yeah.
I would count that as well.
Because they're like, they don't change anything.
Right. So, okay. I'm going to skip C. So I'm trying to get, I want to make sure we get through this, give you guys some work time that are in here. I don't want to make this hugely long for people that aren't in here. So, couple of things here. Let's see. Inverse reflection principle. Okay, one of our topics here is inverses. And graphically, if a function has an inverse, that if we were to graph the function and the inverse, they are symmetric across the line y equals x. Now, can you visualize what the line y equals x is?
Yeah.
What's it look like?
Just a line.
Just a line going what direction?
Going up into the first quadrant and starting from the bottom left of the third quadrant. Right?
Yeah. Goes in the third quadrant and first quadrant. It goes through what in the center?
0.
It goes through 0. It has a y-intercept of 0, if you want to think that way, and a slope of 1.
Oh, 1.
Right? So it goes through points like 0, 0, 1, 1, 2, 2.
Yeah.
It's what you sometimes hear referred to as the perfect diagonal line, because it goes straight through the center, 0, 0, 1, 1, 2, 2, the negatives, any place y and x are the same. Okay. And so that is the idea. We'll look at a graph like this in a moment. Now, inverse composition rule. a function is one-to-one with an inverse function g if and only if fog equals x and goth equals x. So we'll practice that down in example 6. But the idea of a way to prove if a function and a supposed inverse are truly inverses would be to see if fog and goth equals x. And so we will look at that down in example 6. Okay? So 2 things to work with here. Let's look at example 5. They give us this graph on example 5, and they ask us to sketch the graph of the inverse function for the function drawn on the grid provided. Okay. In order to find an inverse, what happens between the function and the inverse? We talked yesterday that the ordered pairs will what? If the function has an ordered pair a comma b, then what does that become in the inverse? Instead of ab, it was ba. Okay? And so the idea that if you have an ordered pair that goes through, say, 5 comma 8, then in the inverse it's going to go through 8 comma 5. Okay, so right here, are you with me now? Okay, so right here, if we look, let me blow up this graph right here. This is the original function. If we want to do the inverse, find some ordered pairs that you can reverse.
Okay,
so
0, -1. Shall we write them down?
Okay. We could. Well, and actually, this isn't 0, -1. This is -1, 0.
Yeah.
And what does -1, 0 become?
0, -1.
0, -1. So that means there's going to be a dot right there on the inverse, correct?
That's why I said it. I just said it. I should have said that first.
Okay. So what about this dot up here? This is a
0, 1.
0, 1. What's 0, 1 going to become then?
1, 0.
1, 0. Put a dot there. I kind of see another dot here that we could use.
1, 2, 2, 1.
Okay. 1, 2 can kind of become 2, 1. Now, this is where it gets a little tricky. You kind of have to use the idea, because right now it looks like we just put 3 dots in a line, doesn't it?
Yeah, but since we're like flipping it.
Yeah, we're reflecting it. Now remember, it reflects across that perfect line of y equals x, right? So if I even draw in, and I'm just doing this lightly in pencil, can you guys see my y equals x line there?
Yeah.
I'm reflecting across that. So whatever my graph is doing there kind of above it, we're going to kind of do the opposite below it, right?
Yep.
And so, first of all, like if I start down here, right here where this is crossing that y equals x line, it's going to cross again. So that's kind of another point because it's going to have to cross in the same place. But the idea is going to look like this. As I go between these 2 points right here, notice this is curved out and away from the origin. So this is going to curve out and away from the origin.
So you basically just reflect it across that y equals x.
Yep.
Okay.
Right here, since this one curves in towards y equals x between these 2 points, I'm going to curve in towards y equals x on this side. This one kind of goes up and away. That means this one's going to kind of go right and away. Kind of like over here, it's going down. Ours is going to go left.
Yeah. Basically, that's being an artist. Since you're like,
I wouldn't say you have to be an artist, just because I definitely am not an artist. But I think with the curvy graph, it makes it a little bit difficult. But think about it. If I were to take this paper and I were to fold it on that diagonal line, does my graph land on top of itself?
yeah.
Yeah. And that's the idea of what should happen. Okay. one last thing. And this last thing is to show algebraically that f and g are inverses. This goes back up to what was right above there, the inverse composition rule. If f and g are inverse functions, then that means they're one-to-one, but more importantly, remember what it said up here? Fog equals f and Goff equals x. Both have to be true. So we can prove this by finding Fog and Goff, your favorite friends, right?
Yeah.
Okay, so algebraically, not graphically, algebraically. So let's start by practicing and finding Fog. Okay, remind me, what does Fog mean? F of g of x. That means I'm going to take g and plug it into f. So if you want to, some people like to say, okay, it's f of, what is g of x? The cube root of x minus 1. So that g, the cube root of x minus 1, goes into f. So what is f that we're putting this into? X cubed minus 1, right? So I'm going to take whatever it is I'm plugging it in, I'm going to cube it, and subtract 1. What is it that I'm plugging in? The cube root of x minus 1. So I'm doing the cube root of x minus 1. That's what I'm plugging in. I'm going to cube it. Whoops, and I'm going to add 1. What happens when you cube that cube root?
Gets rid of that cube root, so that's x minus 1 plus 1.
Okay, so that's going to become x minus 1. We have the plus 1 at the end. And x minus 1 plus 1?
Cancels.
Minus 1 plus 1 cancel, and we're left with x. What were we supposed to be left with? X. So right there, I showed that fog is equal to x. Now, we also need to show, in order for this to be 100% guaranteed, that
The g of x equals x.
Goff equals x. So what does Goff mean? G of f of x. Which means I'm doing g of, what is f that I'm going to be plugging in? So I'm going to be taking f and putting it into g. Which means I'm going to be taking x cubed plus 1 and putting it into g. So what does g tell me to do? Yeah, it's the cube root of something minus 1. What am I putting in place of that something? X cubed plus 1. What do you know about x cubed plus 1 minus 1? Yeah, the ones cancel. So now I have the cube root of x cubed. What is the cube root of x cubed? Just x. And so what did I just prove now? That Goff is x. So I just proved that f of x and g of x are inverses. If I were to graph both of these, they are going to be reflections across that perfect diagonal line. And for instance, I think I want to show you that real quick.
So what are you plugging into? Are you plugging in y equals?
On my calculator?
Yeah.
Yeah, so f of x equals x cubed plus 1. I just plug that in as my y1. G of x is going to be the cube root of x minus 1. That's my y2. And then, just because I want to show you, I'm going to plug in y equals x as my y3. I just want you to be able to see here. Okay, so right here is F. That's blue. In red is G. And then this black line is the line they reflect across.
So you can check yourself. Well, you count the notes, but enough homework is going to give us that graph and then a part B to do the same thing.
I don't know.
Because
Not necessarily.
we know we're right because we got that same graph.
Yeah.
So like, I don't know if like in the homework
Well,
it's going to give us that.
And really what I was just, I mean, they gave us the equations and they told us they're inverse functions. We just had to show it. And so we showed it by the fact they both came out to be X, but I just wanted to give you the visual there of, you know, honestly, I hadn't even really paid attention to the fact that this is what was graphed here, to be honest. So, okay. The homework for this lesson, page 126, 1 through 6, 9 through 12, 14 through 22 evens, and 23 through 29. 14 through 22, I think it says something about domain in the directions. Forget that direction. Okay.
Forget one direction.
If it says something in that